Welcome to the subject Electromagnetic Waves and Transmission Lines. In this session, we shall be discussing the topics conduction and convection currents, then dielectric constant, then the different types of capacitances. These three are associated topics in the sense the dielectric constant is a property of a material. That material is used to fill the region between the plates of a capacitor or between the spheres of a capacitor or between the cylinders of a capacitor according to the geometry of the capacitors. So, before going to these capacitances and dielectric constants, we have a small topic which is a topic which distinguishes the two types of currents, namely number 1 the conduction current, number 2 convection current. Well, you know, current is flow of electrons. Precisely, if you want to give a specific definition of current, then we say the amount of electrons crossing a point in 1 second. This is the more specific definition of current. But basically, in a fundamental sense, we say current is nothing but flow of electrons. Now, how do you get this distinction? Conduction current and convection current. What they actually mean? Where you come across these types of currents? What are the formulae for conduction current and convection current? Because both are currents, but the formulae will be different. The scenario will be different. The context will be different. Let us see that. So, first starting with conduction current. What is conduction current? It's a current which is observed in conductors. The type of current that is observed in conductors. Flow of electric current happening in a conducting material. That is called as conduction current. In fact, that's why we say conduction current. The current happening in a conducting material. So, we say conduction. This is due to the drifting of electrons. When you apply voltage, then as a result of applied voltage, you have some flow of electrons, the drifting of electrons. This is happening in the conductors. So, we say conduction current density. Now, moving forward, what is this convection current? It's also current which exists in dielectrics. Previous current was existing in conductors. Convection current is existing in dielectrics. Now, this is due to the displacement of charges. Due to the presence of electric field, there is a displacement of charge carriers, electric charge carriers. Basically, we say electrons. So, due to the existence of applied electric field, there is a displacement, a change in position of the electric charge carriers. So, that is called as convection current, or also we say it as, there is another name for this convection current, that is displacement current, because that is due to the displacement of charge carriers. So, that is how it is derived, the other name. So, don't get confused. Convection current and displacement current both are same. So, where do you find this convection current? In dielectrics. So, conduction current in conductors, convection current in dielectrics. The other name for convection current is displacement current, because that happens due to displacement of charges. If you want to understand this in circuit analogy, because we are very well aware of the circuit theory, where we have elements which build a circuits. Now, the current flowing in this first case through this resistor, the flow of current through this resistor is known as conduction current. That's why I have written here IC. I means current, C means conduction current. So, basically, what is the formula that you apply for current here? When current is flowing through resistor, V equal to IR. So, I is V by R. That's what I have written here. So, IC is V by R, the basic formula which we use frequently. Now, coming to the second type, displacement current. The current that is flowing through this capacitor, that is known as displacement current. Why? I told the current that existing in a dielectric, that is convection current, I said. But now I am saying the current that is flowing through a capacitor. Here I am saying through dielectrics, here I am saying through capacitor. If you understand carefully, both are same, because this is a capacitor. Capacitor has a property of capacitance. Now, what is there in the region between these plates? Let us say this is a parallel plate capacitor. Between the plates of capacitor, what do you have? You have dielectric material. That means The current is flowing through this capacitor means the current is flowing through the dielectric material within the capacitor. So ultimately the current that exists within a dielectric. So that's why we say this as displacement current or convection current. Not only the context, here we use resistor, here we use capacitor. Not only the circuit analogy is different, even the mathematical formula is different. Here it is V by R, here it is C dV by dt, isn't it? If you recollect, this is the formula that we use for calculating current through a capacitor. So here I write I means current, D means displacement current, or I can say convection current, because if I write here IC, C is convection, already I am using C here to indicate conduction. Again I cannot use C for convection because it gives confusion. So I am using D because the other name for convection current is displacement current. So ID stands for displacement current, which is given by C dV by dt. So the analogy is different, the formula, the mathematical formula that is used to calculate the currents, they are different. So they are basically different types of entities, electrical entities. One through a resistor. Here I say resistor, it is not superconductor. A resistor will have some finite resistance. It is not having infinite resistance, it is having some finite resistance. That means it will have some finite conductance. So current flowing through this conductor. That's why we say it as conduction current. So these are the two types of currents that we come across. Next you have dielectric constant. So before going to the small derivation, I just want to explain you dielectric. Di means two, electric means a property. Dielectric means a material having two properties. Di means two. So what are the two extremities of electric materials? One is a material can be either electric conductor or a material can be electrical insulator. I am saying extremities. Either you have electric conductor or you have electric insulator. No matter whatever happens, an electric insulator will never allow the flow of current. It insulates. That's why we use rubber, wood. They are best examples of electric insulators. Electric insulator will stop the flow of electric current no matter whatever you do. And electric conductor on the other hand, it will have electric conduction naturally, because that's the reason we say it as conductor. An electric conductor will support conduction. Of course, you have to apply some voltage, that's a different thing. Without input you will not get any output, that's a different thing. So you have to apply some voltage, you keep it aside. So an electric conductor will naturally support electric conduction. So for that you have to apply some voltage. It will support conduction. So we say electric conductor. Now for electric insulator, whether you apply voltage or anything, even if you apply tremendous amount of voltage or whatever you do, you will never get conduction. That's why we say it as insulator. So exhibiting conduction is called electric conductor. Exhibiting insulation, we say it as electric insulator. There is one material which exhibits these both properties. That is, a dielectric material will naturally does not allow the flow of charges. However, with the applied electric field, it will start displacing the charges. Flow of charge, movement of charge, displacement, change in position. So this is how we are able to get electric current. Naturally it behaves like, in normal state it behaves like electric insulator, but with the application of electric field it starts behaving like conductor. So it has two properties, dual properties. So not having conduction in one state, exhibiting conduction, displacement of charges in another state with the application of electric field. So what happens is in dielectric materials, so you should understand very carefully this before going to the derivation. In a dielectric material, the charge carriers which are there, they are bounded by the intermolecular forces. In a dielectric material, the charge carriers which are supposed to conduct, they are bounded by the intermolecular forces. Means if the charge carriers have to move, they have to come from the clutches, they have to come out of the molecular forces. First they have to come out, then they can start conduction. So first someone should liberate them. Someone should liberate them out of the molecular forces. Then they can start conduction. So for that, whatever electric field we are applying, that takes the responsibility of liberating these charge carriers. Then these liberated charge carriers, due to applied force, they can displace their position, move, which we try to analyze in terms of current. So these are the technical intricacies which happens inside a dielectric material. Now, dielectric constant is a property associated with a dielectric material. So far we have discussed basically what is the dielectric material, all those things. Now let us understand the property. Dielectric constant is a property of a dielectric material. Like we have what is the property of electric conductor? Conductivity. Like that, dielectric material also has a certain property, and that is called as dielectric constant. Now we are going to understand it in a mathematical sense. Now, what happens if you try to polarize a dielectric material? Because the discussion starts with P bar. P stands for polarization. It's a vector, so I have kept a bar here. Now, what is polarization? Again, we have to discuss some background for this before going to this. What is polarization? Polarization, polarities. What do you mean by polarities? Positive charge, negative charge. They are called electric polarities. North pole, south pole. They are called magnetic polarities. So when you apply electric field, positive charge will try to come one side, negative charge will try to come other side. So you have what do you say as a dipole? Two poles are there, two electric poles, positive charge, negative charge. Similar to magnetism, we have magnetic dipoles. Here you come across electric dipoles, positive charge on one side, negative charge on other side. There are several such dipoles. You cannot get only one dipole or two dipole. When you apply electric field across a dielectric material, you will get several such dipoles. Then the question is, how many dipoles are existing, or how many dipoles are generated or formed per unit volume? No matter whatever may be the size of dielectric material, you consider unit volume. How many dipoles, electric dipoles are formed in a unit volume of a dielectric material? That is known as polarization. That's why if you see here mathematically, P bar is equal to, the numerator you have polarization formed, denominator you have delta V, means per unit volume. That is the actual meaning. The net dipole moment formed per unit volume. That is the actual meaning of Qi by delta V. And what is this Qi into Di? As I told you now, there is no single dipole. There are multiple, or I can say several electric dipoles that are formed due to the application of electric field. So if I take I equal to 1 here, if I take I equal to 1, what do you get here? Q1 D1. Take I equal to 2, Q2 D2. That means Q1 D1 indicates first dipole, Q2 D2 indicates second dipole, Q3 D3 indicates third dipole. How many such dipoles will be formed? That's why I have taken I equal to 1 to N. But they are corresponding to a unit volume delta V. That's why I have taken delta V into delta V. Now, Q stands for the magnitude of any one of the charges. We have positive charge, negative charge, equal and opposite charges on either sides, which is called as dipole. So, two equal but opposite charges separated by some distance will form a dipole. If the two charges are electric charges, that is electric dipole. If the two charges are magnetic charges, that is a magnetic dipole. So, two equal but opposite charges which are formed having certain distance, spacing d. That is the meaning of Q into D by delta V will give you polarization. Well, what are the units here? I have written here coulomb per square meter. Why? The reason is, what is the unit of charge? Electric charge, coulomb. Unit of distance, meters. Unit of volume, cubic meters. So, these meters cancels, you get coulomb per meter square. That's why I have written coulomb per square meter. Now, this unit of polarization P bar happens to be the same unit as D bar. Recollect, what is D bar? Electric flux density. Flux per unit area. The amount of electric flux crossing a unit surface area normally. This is the actual definition. But in a simple sense, we say electric flux is flux per unit area. Electric flux has the same unit as electric charge, coulombs. Per unit area means coulomb per meter square. Notice the unit of polarization and the unit of electric flux density are same. Which also means, if you go back in a reverse way, which also means that if you polarize a dielectric material, then the flux density will also increase because dimensionally they happen to be same. So, a polarized dielectric material will exhibit more flux density than a unpolarized dielectric material. That is actual meaning here. Now, coming to the actual derivation. So, you know D bar, the electric flux density after polarization, what will happen? You know D is epsilon E. Let us take the median to be free space. For simplicity of analysis, I am writing here. So, D is epsilon E. This is a normal relation. Plus P bar. Because after polarization, the polarization component also adds to the flux density. Because a polarized material will exhibit more flux density. So, I am attributing this P bar to this first term. So, D is epsilon E bar plus P bar. Now, what is actually P bar? Polarization. This is the definition and theoretical understanding for that. The polarization is xi E epsilon E. D bar is epsilon E. P bar is xi E epsilon E. Now, what is this xi E? It is looking like X. It's not X. It is xi. The Greek alphabet xi. Xi stands for the susceptibility. Here I have written E. E means electric. So, how do you understand this xi E? Electric susceptibility. E means electric, xi means susceptibility, electric susceptibility. Well, what is this electric susceptibility? Susceptible. What do you mean by this word susceptible? Means which is prone to change. It can be changed easily. Susceptible to change. The electric susceptibility indicates how easily a dielectric material can be polarized. If I say A is a material whose susceptibility is 10. Let us say it is a dimensionless quantity, doesn't have any units. Let us say A is a material whose susceptibility is 10. B is another material whose susceptibility is 100. Higher the susceptibility, easier the material can be polarized. Or I can say higher the susceptibility, sensitive is the material for the polarization. Means the materials with higher susceptibility are more sensitive to the applied electric field, so they can be easily polarized. The materials with less susceptibility cannot be so easily polarized because they are not so sensitive to the applied electric field. So, higher the susceptibility, easily the polarization can be achieved. That's why they are directly proportional. Then you have electric permittivity, then you have applied electric field, because without applied electric field you don't get polarization, you get flux density. First of all, that should be there, source should be there. So, that's why electric field will be there anyhow in D bar and P bar. E is common, that is inevitable, that is required. Now, take this equation. Now, you know the expression for P bar. Substitute this P bar expression here. Then I get this expression. So, D bar is epsilon E bar as usual plus substitute for P bar xi epsilon E bar. Now, in this, what is the common term? What is the common variable? You have epsilon, which is common in both the terms, first term and second term. Epsilon is common. Then you have electric field, which is also common in both the terms. So, I have taken that outside. So, D bar is epsilon E bar. I have taken outside, which is common. Then what remains here? Take this 1 plus xi. So, 1 plus xi. Then now compare here. The general expression, the basic expression for D bar is D bar equal to epsilon E bar. D bar is epsilon E bar. But what is epsilon? Epsilon naught, epsilon R. The same thing I have written here. D bar is epsilon naught, epsilon R, E bar, epsilon naught, epsilon R, E bar. Now compare them. You have E bar, epsilon naught, epsilon naught. So then what epsilon r should be? Epsilon r should be 1 plus xi e. On making one-to-one comparison, that's why I have indicated with pink lines. We have one-to-one correspondence, epsilon naught, E bar. So the remaining is epsilon r, which is 1 plus xi e. So the R means relative, epsilon means electric permittivity. The relative electric permittivity is susceptibility plus unity. One means unity. We know epsilon r is also known as dielectric constant. We use the symbol K for dielectric constant or epsilon r. Both are same. The relative electric permittivity is nothing but dielectric constant, which is 1 plus xi e. So this is the expression for dielectric constant. Next, we move on to the topic capacitance and the different types of capacitances. Well, you have 3 types of capacitances in your syllabus. Number 1, parallel plate capacitor. Number 2, coaxial capacitor. Number 3, spherical capacitor. 3 types of capacitors you have. Now, what is capacitance basically? This you have been studying from your school days. Intermediate, high school, you study capacitance. Q by V. Capacitance is an electric property. That's why we say capacitor holds energy in the form of electric field. Capacitor is an energy storage device. What kind of energy? Electric energy. So what is capacitor? It's an electric device. What is capacitance? It's electric property. So we say electric capacitance, electric charge, electric potential. All are electric because the first chapter is nothing but electrostatics. So how do you define this? The electric capacitance is defined as the ratio of, because you have a numerator and denominator. So it's a ratio. The electric capacitance is a ratio of the electric charge to the electric potential. Electric charge means you can take charge on any one of the plate of the capacitor. If you have parallel plate, you have 2 plates. Q means charge on any one of the plates. One is having positive charge, another is having negative charge. The polarity may be changing, but the magnitude will be same. So the capacitance is defined as the ratio of the magnitude of charge to the potential difference between the plates. Now, first case we have parallel plate capacitor. As the name suggests, you have 2 plates which are parallel to each other, which forms a capacitor, which is called parallel plate capacitor. You can observe the geometry. There are 2 plates. This is plate 1, this is plate 2. One is positively charged, another is negatively charged, equal but oppositely charged. And the spacing, the distance between the plates is D. Each plate has certain cross-sectional area, that is A. This is positively charged, so I have taken here positive. Rho. Why I have taken rho? Because the charge is spread on the area of the plate. So it is charge density. Charge is spread on the area of the plate. So charge per unit area. That is called surface charge. That's why I have taken here rho s. Of course, here positive charge, so plus rho s. Here negative charge, minus rho s. So how do you determine or how do you evaluate the capacitance of such geometry, parallel plate capacitor? That is given by C equal to epsilon A by D. Epsilon is the permittivity of the material that is filling the region between the 2 plates. A stands for the cross-sectional area of the plates. D stands for the spacing between the plates. You know, electric lines of force start from positive charge, end at negative charge. That's why I have taken arrow here like this. They start from positive charge, end at negative charge. So the arrows are going up. So this is about parallel plate capacitor. There is another type of geometry which is available in capacitors, that is coaxial capacitor. First you understand. Coaxial. Why do you say axis? This is inner conductor, let us say, and this is outer conductor. For circle we have center. For cylinders you have axis. So this is the inner conductor. Let us say the inner conductor is lying along this axis. This is the axis along which this conductor is lying. This is also the axis for the outer conductor. The outer conductor is also lying along the same axis. So two conductors sharing the same axis, we say co-axis. Co means sharing. Co-education means girls and boys sitting in the same class. Co-education. So inner conductor or inner cylinder or outer conductor sharing the same axis. So we say co-axis, coaxial. So this is called as coaxial. And the region between the two conductors. The region between the two conductors is filled with a dielectric material. It forms a capacitor. That's why we say coaxial capacitor. The radius of inner conductor is A. The radius of outer conductor is B. If we have two conductors, so we have two radii. One is A, one is B. A stands for inner radius. B stands for outer radius. That's what I have labeled here, A and B. And the region between these two conductors is filled with dielectric material whose permittivity is epsilon. And the length of this coaxial capacitor, I have written up to here, so I have taken L. It can be even more or less. So the length of this coaxial capacitor is L. So they are the parameters you find. L stands for length of capacitor, epsilon stands for the permittivity of the material that is filling the region between the two conductors, inner and outer conductors. A stands for radius of inner conductor, B stands for radius of outer conductor. So what do you understand from this? The capacitance of a coaxial capacitor depends on the length of the capacitor. Bigger the conductors, bigger means in the sense of length. Bigger means not in terms of radius. Bigger means how big in terms of length I am saying. Bigger the coaxial capacitor, higher will be the capacitance. Higher the permittivity of the material that you are using, higher will be the capacitance. Next, you have in the denominator log B by A, logarithm of B by A. B by A stands for the ratio of outer conductor to the inner conductor, which simply means that the radii of the inner and outer conductor will not individually decide the capacitance. Together they will decide the capacitance, together in the form of ratio B by A. It doesn't matter what is the size of B, what is the size of A, means what is the radius of inner and what is the radius of outer conductor. That doesn't matter. Instead, what matters is what is the ratio of the radiuses. That matters. So higher the ratio, what will happen? Let us try to understand. If the ratio of outer conductor to inner conductor is more, let us say see these two diagrams carefully. Here let us say inner radius is 2 millimeters, outer radius is 10 millimeters. In this case, the inner radius is 2 mm, the outer radius is 5 mm. So what matters is the ratio. Here 5 by 2, it is 2.5. Here 10 by 2, it is 5. So in this case, the ratio is more. So higher the ratio, higher will be the denominator. Higher the denominator, lesser will be the ratio. Why? Because if the denominator dominates, the ratio falls. If ratio falls, capacitance falls. So you should not take the individual values of the radius. You take the ratio, that will decide the amount of capacitance. Next, the last and the final one, that is the third one, is spherical capacitor. As the name suggests, you have two spheres. Parallel plate capacitor means you have two plates. Spherical capacitor means you have two spheres. It is given by, like you can see here, inner sphere, outer sphere. The radius of inner sphere is A, radius of outer sphere is B, similar to the previous case. Now, what is the capacitance? 4 pi epsilon. Epsilon means the electric permittivity of the material that is filling the region between the two spheres. Inside there is one sphere, outside there is another sphere. The region is filled with some material, its permittivity is epsilon by 1 by A minus 1 by B. So this is the formula for spherical capacitor. Let us try to understand how do you calculate these capacitances. Like for coaxial I have said 2 pi epsilon L by log B by A. For spherical I have taken 4 pi epsilon by 1 by A minus 1 by B. So let us take one capacitor and let us try to deduce. Let us try to deduce the expression, how we actually calculate the capacitance of a particular capacitor. First we will take, for example, we will take spherical capacitor. We will take spherical geometry. The procedure of calculation of the capacitance of a capacitor remains same. The procedure will not change. But according to the geometry, we substitute the appropriate expression. Procedure will be same. So that's why I am selecting spherical capacitor as a case study, and I will try to deduce the expression for capacitance. What is the capacitance of the spherical capacitor? 4 pi epsilon by 1 by A minus 1 by B. How do you get this expression? I will explain you. Now, first, if you want to calculate capacitance, what you require? C equal to Q by V. Q is electric charge, V is electric potential. So you can substitute Q directly. First, we have to calculate the electric potential for spherical capacitor. So I will start with V. After getting V, then you can divide Q with V, then you get this, the previous expression. So V equal to, first write the basic expression for V. V is minus integral E dot dl. You have seen this in the previous sessions. V is minus integral E dot dl. This is the starting point. Now, E stands for electric field. What is the electric field expression? Q by 4 pi epsilon R square is a vector. So, in radial direction, A bar R. Dot. Next, what else you have? dl. dl stands for differential length. The differential length along radial direction, R component, because if you observe the electric field, the electric lines of force are going, these arrows you can find blue color arrows, the electric lines of force are going radially outwards. For a sphere you have R, theta and phi. What is the direction of electric lines of force? Along R direction, radial direction. So the differential length along R direction in spherical system, because we are taking spheres, spherical system is dr AR. So for a dl I have substituted dr AR. For E bar I have taken the expression Q by 4 pi epsilon R square AR, basic expression. Now AR dot product of two vectors, identical vectors, same 1. AR dot AR is 1. Then you have Q by 4 pi epsilon, which is constant. I have taken outside. What is remaining here? 1 by R square. Integral 1 by R square dr. What is it? Integral 1 by R square minus 1 by R. And what are the limits? Limits of R? R equal to B to R equal to A. Why B to A? You can observe here. The radius of outer sphere is B, inner sphere is A. So from here to here, the region from B, this is B, from here to this is A, from here to here, because the electric lines of force and electric field exist there. We are trying to substitute the limits of R. Why? Because R goes from B to A. What are the limits of R? R is nothing but radius. Outer radius is B, inner radius is A. In the definition of electric potential, what is the definition? Electric potential is defined as the amount of electric work done in moving a unit electric charge from one point to another point against the electric field. Against means, if you observe carefully here, this is the direction of electric field. Against means this way. This means going in. Going in means from B to A. That's why I have taken B to, from B to A. B to A. If you substitute the limits for R, you have 1 minus here, 1 minus here. So you get plus Q by 4 pi epsilon. Limits of R, substituting for R, 1 by A minus 1 by B. This is the expression for V. Now we got V expression, but what we want? C. C is Q by V. So divide Q, electric charge, with this expression V. So C equal to Q. As it is, I have taken Q by V. V means this one, this entire expression. I have taken the denominator. So Q cancels. You have 4 pi epsilon. This goes into the numerator. 4 pi epsilon 1 by A minus 1 by B. So this is how we get the expression for capacitance. This procedure remains same for every type of capacitor, no matter whether it is parallel plate or spherical or coaxial. Irrespective of the geometry of the capacitor, the procedure to evaluate the capacitance remain